Hello everyone. So, do you get your homework done? Assignment? So, assignment, I think 2 questions, right? The first one is the polycarbonate, the bisphenol A and the phosgene. And I'm asking, I think most of you did a good job because phosgene or bisphenol A, the reaction is quite popular. So if you look on, maybe if you type in the Google, you will find mostly everything. And I think still, if you compare to today's synthesis, although the reactions is dangerous, up until now they are still doing that reaction because in terms of polymerizations, they have the good conversion from monomers to polymers, and then I believe we can produce like a large amount of the polycarbonate easily through the bisphenol and phosgene reaction. Okay. So this is what we have learned before, the polycondensation. And one of them is polycarbonate, which the idea of the condensation is having a small molecules that is releasing when we polymerize the monomers. So the small molecules can be anything, can be water, usually water, can be an acid or a base or any other, or maybe salt. But the idea is there will be small molecules. And I think the second question I'm asking you in assignment is the alternative on the aromatic polyamides. Right? I think you could try to find out. Because there are several options that the materials they are maybe developing. Maybe they will develop the more sustainable or more high performance fibers, like the ultra high molecular weight of the polyethylene. That is also one of the choices, aside from the aramides, the aromatic polyamides, and they are also provides good mechanical properties, especially for the tensile stress. Okay. Now let's go to, still this is also some other polycondensations with the aromatic polymers. With aromatic polymers, we have the polyamide, the PBO, also the xylone, but I think not really in our course. So the next one is the poly addition. So without the elimination, so it will be the monomer react and then a polymer without any small molecules that is releasing. Okay. So we call that a poly addition. The best example for poly addition is the polyurethane. So let me take this for a while. The reactions. So you have a diols. This is a preparation for the, I think, for the monomer. So we have this diisocyanate. This is diols, and I think this will be the catalyst. But I think there will be some differences when we look on more general. So let me just give you the the idea on how to describe this polyurethane in more general. So polyurethane, and let me describe this also. We could also make a different set of polyurethane that is having a foam. Okay. So this is how it works. So we add water, and the water will react. Okay. The water will react, and imagine when the water reacts, then practically they will polymerize by itself, okay, with the help of water. Here, so the result is react again with the isocyanate. So water, isocyanate, getting this NH amine groups, and the amine groups react again with the isocyanate. Okay? And then we'll be creating the polyurethane, but with the structure of foam, okay, because of the water. Let me explain that to you. So this is polyurethane standard reactions. So usually we are going to have diisocyanate and then diol, as mentioned here. Okay? It's diols, 2 alcohols, and diisocyanate. It has 2 isocyanate, right? This and this. Okay. So this is a standard reactions, okay, for the polyurethane. Let me write again the reactions. Sorry. Wait. Let me write here the isocyanate is R1. And then plus the diols, okay, and then in oxygens we have electrons here, right, and in the diols we have electrons there and there, right. So let's focus on one end. Okay, let's focus on one end. That is, remember, since the oxygen in the isocyanate here having electron, which means that the carbon here is more positive, right? Okay. And then since this is also negative, this carbon has attracted, okay, because this is also negative. So it's unstable at its position, so it will be attacking. So this oxygen will attack this carbon, okay? This electron will attack this carbon. We call that nucleophilic attack. Nucleophilic attack. Okay? There will be a common terms in the later courses as well. If you learn, I think that should be in the, if you learn organic chemistry before, I think the course mentioned that as well. Okay? And also in the later course in polymer chemistry or other polymer courses, they will have these terms. Okay, so we have nucleophilic, we have the electrophilic. So nucleophilic is when this is the electronegative. This is attacking this carbon here, which has more positive, okay, compared with the oxygen. Okay, so this is nucleophilic. Okay, the idea is still the same as we mentioned before in the poly condensations. So when we attack this part here, then the bonds will break. The bonds will break, and then this will be here. Let me write with just R1, focus on the right side, just to give you illustration here. So this is the oxygen from the first, and this other oxygen is from the diols. Okay, so this is diols, and this has the H as well. And again, we we need to look at the electrons. Okay, so it's not yet finished. Okay, so do not conclude that this is the reaction, and you see this is having 3 bonds. Why? Right? This is just in the middle of process. We haven't yet finished. So I want to show you how the bonds will broke. And from this part, to stabilize, these electrons will go here, will go out here, and then the bonds with the hydrogen, this is also going to here to stabilize, and the nitrogen now, okay, it has also electrons here. This is also going to go there, okay, to stabilize. This double bond is going to broke. Okay, so this is to stabilize the reactions. The result, so the hydrogen will go to the nitrogen, and then this will be having the double bond on the oxygen, and still this is the oxygen here, single bond, and then R2, and then OH. This is this part. Or maybe that part with R2. So if you look at this will be what we have in here. This is what we call as the urethane, the repeat units. The name is it came from this unit. And then if you see the difference between these reactions compared with the previous one, they are all perfectly matched with this. So diisocyanates will react perfectly with the diodes, and they will not releasing any small molecules. They will not releasing any small molecules. So attacking from this part is stabilized, making the double bond broke, okay, and making this more dense in electron, and then it's connecting the oxygen here, going there, going to the fifth carbon, and since this is already in a bond with the oxygen and nitrogen, then they need also to stabilize this large electron here, right? This large electron, maybe they will go here. It's not going here, making a double bond, and then because it has double bond, the double bond here needs to go away because it's already full, so it needs to go away. So it's going here, it's becoming a free electron, and the free electron needs to combine with other molecules, and the other molecules that is in terms of energy significantly low is this hydrogen here. So they take this hydrogen, so that's why the hydrogen moves from this oxygen go to here, and this will release the bonds and making the connections to the other diodes. Now polyurethane, where you can get the polyurethane, do you know? What kind of equipment?
Medical.
Yeah, medical. I think some clothes will be polyurethane, some clothing. What else? I think like for acoustic, like the insulations is also polyurethane, like for wall to make not noisy. Maybe to reduce the noise, you put the polymerization. So polymerization is one type of polymer that is really wide, okay, wide variations of the usage. Okay. So you can use it for medical, your clothes, some of it also for some, I think for some rigid materials like on installations, maybe for protections also. You can use the polyurethane. Because I personally use the polyurethane in medical fields for making the synthetic vascular grafts for your blood. It is also from polyurethane. So it can be used for clothes, medical, coatings also, and like in the foams for insulation, for example. Okay, and then if you can imagine how the polymers will take the forms after this structure, this bond, the origin bond, this OH, the OH will be react again. The OH will be react again, and will be taking as a backbone for the polymers. Okay, so this will be the backbone, okay, and becomes this. And it's repeated. And the left side also, they also react, okay, go there. And that's why it has this repeat unit. Okay, so I hope after you get the idea, okay, I hope you can review and try to understand how this is going to work. Okay, how this is going to work. So the idea is every free electron, every unpaired electrons, they will have tendency to attract, okay, or to go to the positive side, okay, because they are negative. Or to be precise, we say this is electronegative, more electronegative than this part. Because both of them are electrons. If I say it's more positive, maybe you will get a wrong perspective. But I will say this is going to be more electronegative than this part here. So that's why it goes from this negative go to this carbon. Okay, that's attacks, we call it nucleophilic attack, and then the double bond will collapse, making this oxygen has a lot of electrons, and they need to stabilize, and they need to go here, and it will be making this carbon unstable, especially here. So this is going to also release. And then we have the electrons that need to stabilize. So the electrons easily to stabilize with this hydrogen here, and then it's easy to release, okay, because the energy for this bond is lower than this part, so it's easy to go there. Okay. Okay. this is most common use diisocyanates and some of the diols. So look at the idea here. We have three different isocyanates: MDI, HDI, and TDI. They have difference in the structure. For the first one, they have the aromatics. This is what we had before. Usually, this is the standard. This is the standard. It can be hexamethylene diisocyanate. And this one is, we have two different structures, diisocyanate toluene and toluene diisocyanate. So they can be mixed. So they can have this structure here. The difference is here in the isocyanate. It has different in the number. But the reactions will be the same. So we just focus on this bond, this double bond here, which is going to break if we add the diols. The diols can be, for example, this is actually there is more, but this is just a typical chemical. So this is diols. This diols like we did before, and this one is another diols, which has more aliphatic chains in the middle, and we have another oxygen in the middle. But still the same. The reactors is just the end group. Okay. So I need to maybe emphasize in the step polymerizations, all the reaction you see is left, right, the bifunctional or difunctional monomers. Okay, that's the key. Okay. So all the step polymerizations, most of it, if we want to make it into linear chain, we need to have difunctional. Okay. So most of the linear chain will be made up from that kind of reaction. Okay. So this is the end group, right? This is also the end group. So this is the one that will be a react. Okay. Okay. Let me write. What is this? Okay. Let me write the foam reactions. Okay. Let's say we have the isocyanate. This is double bond and double bond oxygen, and plus water. Okay. So to make a foam, we need to react the isocyanate with water. If we draw water like this, so we have free electrons. And remember, in water, we have this unpaired electron on the oxygens, which is also can be considered for the nucleophilic attack as well. So if we take this as oxygens having a free electron there, so we have, again, this is electronegative, that is positive, this is more electronegative. So we could take this going to there. This will be some nucleophilic effect. The results, let me draw all and then explain with the arrow. So this will adjust the structures, okay? And again, because we have large dense electrons here on the upside, we need to stabilize. So they will go here to stabilize, make it the double bond. And then in the carbon, we have 5 now, so it's not stable. So we need to break the bonds, okay? Break the bonds here, and then it's become a free electron there. That need to be reacted to the hydrogen. It's the same with before, the same. And then this is going to break, right? Or let me write there, break the bonds, and the H will move to nitrogen. Let me draw first the result on the right side. So and this will be the hydrogen that is from the below, and this will be the carbon, and this will be the double bond to the oxygen, and this is another oxygen, and this is, and still we have now some electrons there. And of course, if we look on this, so we have electrons there. Now the same thing for this nitrogen, it can also attract this hydrogen. And then makes this electrons goes here to make it more stable. And then because of that, this bonds here needs to be released. Okay. So this is a little bit different. This the last part a little bit different. So the results we will have so the N will totally separate. It becomes NH2 becomes amine, and this will be the carbon with double bonds of 2 oxygens. Okay, that's the results. But further, this amine is still can be reacted. So imagine the amine and the isocyanate, they will react. So this will react with this. So let me write here. NH2 plus the, let's say the O, let me write OCN. And again, similarly, this amine acts as the attackers to that C, and it's releasing the double bond. And further, this will getting this is having an unpaired electrons, and the total here, this is positive, this is negative. Okay, the total ions there. So similarly, we are going to make it stable, goes here to make it double bond, and then the double bond here will release, and since it's released, the electrons getting here will connect to the H. So it will stabilize and makes the, so it adjusts its own structure. Wait. So you will get N, C, and it's N, and then this is H, and the double bond of oxygen. And this is what we call the urea. So I think in all synthesis, if you want to work on synthesis in the future, functional groups is really important. And why it's important? Because you can predict the reactions from the electronegativity, how much unpaired electrons they have, and what kind of structures you want. That will be the reasons for the synthesis. Okay. So this is for the foam, polymer. So it's isocyanate and water. Okay, so my suggestions after the class, if you want to review, my tips is go to the macro galleria. You can ask everything about polymer on that website. And you can also ask most basic reactions like we did in the step polymerizations. I think they provide most of the materials. There are actually one more on the step polymerization, which is the polysiloxane, because the polysiloxane is more, you can have a network and like a rubber. I will keep that in the next lecture. But it can be also considered as a linear chain. Okay. Now the next thing, my plan today is to give you. This is other polymerizations using other methods. We call this is Diels-Alder reactions. Okay? Diels-Alder reactions, but this is not really standard in the step polymerizations. So we keep this as a other method. Okay, other method. So Diels-Alder basically will be involving the aromatics group, or will be forming aromatics group. Basically, we are going to have a configuration of a double bond, and because double bond has a lot of electrons in the bonds, so how to cyclic these electrons? So basically, if we take this double bond, and if we have another double bond here, and if we push them to react, then the electrons will move around, and suddenly this will go through this connection, which form the aromatic dienophils. The same with the second one. We have the double bond here, which is let's say a precursor to the aromatic that we are going to form here. And how to make the cyclic electrons? We give them the aromatic. So it's called the Diels-Alder reaction, but not a conventional step polymerization. But still, we can consider that as a poly addition method. Okay. Okay, so our schedule. Okay, so we're still in the step polymerization. Okay. If we can move to another section, so step polymerization will be divided by two. What we have now here is the linear. linear step polymerization. Other sections will be non-linear. Also a lot, contain a lot, like this, the linear one. And after that, we move to the, we call it as chain growth or free radical polymerization. So after we finish, so first we learn introductions, the principle, the step polymerizations, linear and non-linear, and then chain growth. So that is the contents for midterm. So after that finish, we will have a midterm. So we're still in the, I think still in the middle. So probably the midterm will be maybe second week or maybe third week of April. Between that yeah, I think the calendar in the first week, but I think consider our progress maybe not the second week, maybe second week, second week of April. Okay, now if we move on to the next sections for the linear step polymerizations, we are going to learn on the carothers theory. Okay, so carothers theory. So this theory will tell you the relations between the molecular weight and how to predict the reactions. Okay, the first thing, okay, if we look here, this is how we look on the evolutions of the molecular weight. And the x is the conversion, okay, how much the black dots here change to blue or is purple, maybe blue, yeah, blue, change to blue from 0, and then you have 25% of blue, and 50%, and 75%. Okay. So what will be the consequence of this monomer? So when the conversion is larger, and imagine that this will be your polymer chain. Okay. So if the conversion gets larger, like 75%, the chance or the probability you will have the longer chain is also increased. Okay, so that's the idea. So whenever you have a conversion, the highest the conversion it is, the chance to get long polymer chain also increase. Okay, so longer chains it will produce at high conversion. So now from this terminology of the conversions, you can predict the chain. How to predict the chain? We are going to predict the chain. We need a method. To predict the molar mass or the molecular weight of the polymers. And for the carothers theory, the assumptions that need to state in mind is we need to take AB reactions, so only two. So this will be the repeat unit. So that's why to make those AB repeat unit, we need to have difunctional groups. Difunctional of A, difunctional of B. Okay, now, okay, so this is the conclusion. Develop simple method for analysis to predict the molar mass of polymers. So here's the theory. Okay. So first deals with, remember the carothers will deals with this repeat unit AB. We can also look at here. We have a degree of polymerizations, which is just a ratio of the molecules of the monomer, which is the N0, initial monomer, and the N or NT, this is the remaining after some times. Because if we look at the picture before, we have a conversions, right? And there will be some that is not react. Okay? And then to give you an idea of the conversion, we have this P. This is the extent of reaction, or we can say it's the conversion itself. So how many functional groups react over how many functional groups present. Okay. So simply, how many that reacts is just this difference on the initial and then after reaction, right? Which means that is the process. So number of functional groups that have reacted is just N0 minus the N. Okay. So the initial monomer minus the one that has remaining, the monomers that left. Okay. So the difference between this is the one that reacted, right? And then over the initial monomer. So that's the idea. Okay. So that's how we know how much the reactions is converted. And through some simplifications, we could simplify this and making N0 over N equal 1 over 1 minus P. And this is going to be our degree of polymerizations, which we can simply change and substitute. So degree of polymerization is 1 over 1 minus P. Okay? And then look at some notes here that I wrote, that these equations should be applicable or only applicable to the RA2 plus RB2 or RARB or RA2, okay? Which means all of this will make a bond of AB. So this is the assumption. So we need to make assumption that the bond that is reacted or the one that is going to be the repeat unit is AB. Okay? So you can imagine RA2 like this one. And B. So these reactions, this is also forcing to make a single bond for A and B, okay? Or A RB and also ARB. If we consider A and B will be react, we can also make this and force these two to make this unit. Okay? So that's the assumption. Okay? So the linear is assumed when we take AB as a repeat unit. That's why most of the time, from the polyester, nylon, and so on and so forth, we see a lot of difunctional monomers. You see the N groups, okay? two different N groups or the same N groups, okay? Because we want AB reactions. I think we have a break. We have a break. Okay. 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 By the way, regarding your homework, I need to mention it is best give the homework not only gives explanation in words, if you can show some reactions, that will be better. That will be better. And then you can also learn from those you wrote, right? I hope you wrote, like you read before and before you writing in your paper and send. So giving the reactions, I believe if you see the reactions like some polymerizations, like in step polymerizations, polycondensations, and any method, if you see the reactions, rather than writing with the words by words, it will give you more clear explanation directly from the reaction itself. If you can apply that, you can imagine like why the phosgene dangerous. Like, why it makes dangerous? Because when you because it's really reactive, and when your respirations, it's when the phosgene came to your respiration system, it will go in a second. It will go directly to your lungs, and because lungs has some humidity, right? Your lungs have some humidity, and it will hydrolyze directly. That's why it will. Your lungs will be full of water, and it will be full and pass away immediately. Okay, that's why it's really dangerous. If you see, I'm not sure if you can find like a video in YouTube or something somewhere else. If you want to react the bisphenol A and the phosgene, you need to wear like a special equipment so that your respiration system will be protected. Like you have to wear protective equipment. Okay, now go back to this carothers theory. Okay, so they need to assume the AB repeat units, so you can have this kind of type of monomers to make some the polymerization, and they need to have the balance in the stoichiometric reactions. They need to have a balance, especially for the functional groups. In the functional groups, and then usually the values for the P should be as high as possible. So if you have like 0.99, this is a typical in the step polymerization. So you need to make sure the conversion is high as possible so that you can predict the molecular weight. And like mentioned here, so high and pure monomers, and then efficient chemical reactions. Okay, two points, okay, for the reactions. Okay, and then move on that if we want to calculate number average for molar mass, let's say some n, then we could just multiply the molecular weight or the monomer with the degree of polymerization. Okay, so the monomer, we could get the molar mass of the repeat unit over the number of the monomer units. Okay? Or you could say it's the molecular weight of the monomer. And in a stoichiometric imbalance, if they don't have balanced reactions, they will limit the degree of polymerization. Because if you not in a stoichiometric, there will be something left that is not polymerized, right? If not balanced. And then the other part of the theory is using the ratio. Okay? Using the ratio. Okay? So imagine we have A and B, as usual, A and B. A and B is the functional groups. Okay? A and B is functional groups, different functional groups. So if you take the ratio as R, okay, if this is equal NA over NB, and they are the numbers of A and B functional groups that is present initially. And since we have A, B, two types of functional groups, so we could take the average or the initial N is NA plus NB divided by 2. This 2 is because A and B is two different functional groups. Okay, Now the next thing from this R and these relations, now we could rewrite this in terms of one or another. For example, if we want to make an A equal R and B, right? So we could substitute an A with R and B. So from that point of view, we could see from A or from B. So of course, if we are going to take some end at T, for example, that means that this end A, this is going to be true as well at some time, after some time. This will be the approach, the approximations. Or we could simply change this with NB 1 plus R over 2. Okay. Okay, let's continue in a new page to see the reactions or to see the equations. So this is what we have before. Okay. And now we could calculate these two groups. So of course, A and B, there will be some unreacted groups. Okay. We can find that from P and A is the conversions and the conversion of A. So this is the difference on these two. Okay. And then you can rewrite one of them into another one. Okay. And let's write all with terms NB. Okay. Write in terms of NB. And then substitute all the reactions, substitute, and R and B here. We solve this first. Factorize NB. We have this reaction or this equations, and then remember we have the Xn is, or the degree of polymerization. We have N0 over N, and we could rewrite this Xn inside the formulations. So NB, and we're going to take away and then write the degree of polymerization. So let me explain here that this here is start from here and then put all the equations. This is NB 1 plus R over 2. This is NB 1 plus R minus 2 RP over 2, right? And then all the terms will cancel. 2 is cancelled. So that's why it's going to be this. So we could predict the degree of polymerization from the ratio of the molecules, the two molecules, right? The two functional groups A and B, and also from the conversion, the P. So usually, the typical of the graph for the from this carothers theory. If this is the degree of polymerization, this is P, we are going to get something like that. So what's the meaning of this graph here? It is the same as we mentioned as in the earlier class, which when we have high purity monomers, high conversions, the chance that is going to polymerize in a longer chain will be very high. So it's going to be like that, and significantly higher if we get closer to 1. Gets closer to 1. So usually the demand values for the polymerization for the P is 0.99. So the step growth first need to be high conversions. Okay, so need to be high conversion. This is the P, right? And then need to be balanced stoichiometry. So if these two can be adjusted, then the polymer that we want is first pure, and then we can produce more high performance polymer. So that's why more high performance polymers can be prepared from the step growth polymerization. Because in step growth, usually we will have a high conversion to make the polymerization happen. Okay, now next is example. Okay, so what I want to tell you here is the conversions. We have different conversions, okay, and different of the polymerizations. The degree of polymerization. This is the xn, and this is the ratio. So you will see, if we take different ratio and then take different conversion, for example, we take maybe 0.9, okay, 0.9 conversion. The ratio is 1, so let's say it's 1. The polymerization is just 10. Okay? But when we increase the speed, it becomes 20. Increase to 0.99, it becomes 100. And increase close to 1, we get 1000. And eventually, when we have, this is close to 1, let's say we are using the calculus, using limit, and we have the infinite, which means that the more close to 1, conversion is close to 1, we can have as much as possible for the polymers. Okay. So the number of the unreacted monomers become less and less and less. Almost zero. All the monomers are reacted. Okay. This is just to show you that how the conversions will be really important. And the R, the ratio between A and B, is not that significant as the conversions. If we look at the P equals 0.9, if we change the R, it's not much different, right? From 6.9 0.8, 8, 9, 10, 10 is not much different, right? Still, the digits not really that different. But you take to the right, it will be really, really different. But of course, we will have some requirements. For example, if we have R 0.9, okay, 0.9 R, so 6.8, 10, 16, 18, 19, also not very much, right? Because here, the stoichiometry is not balanced, right? Okay, so R is for the stoichiometry. Okay. If you remember what I said before, so R is to give you idea of the stoichiometry, stoichiometric balance, and P is for the conversion. So we need to find where exactly the stoichiometry is getting more balanced. So for example, maybe at 0.9, the stoichiometry is not that balanced, okay, because we see that it's not much different when we increase the conversions. Okay? But then, if we get the, let's say, 9.5 or 9.9, let's say 9.9, we get significantly increase, okay, from 9 until 100 here. Okay? And then if we increase again the ratio, getting more balanced, the ratio, we get thousands. Okay? And if we increase, imagine that it is really, really balanced. The stoichiometry is 1. Then it's really, really perfect. When we have high conversion, high balance, it's going to be infinite in the theory. It will be infinite. So what we need to take to make the step polymerizations, the conversion needs to be high as possible, and stoichiometric need to be balanced. So right here, so step polymerization. We need to conclude that this need to have high conversion, and make sure the stoichiometric balance. Or this is, to be precise, not only step, but this is linear step polymerization. Linear step polymerization. Okay, and then the next thing is the process. Okay. So the process here is, well, let's say some conclusions regarding what we have done before. So the conclusions from the last table, you see that if you want to make high molecular weights, the polymer, we have two conditions. First, high conversion monomer, balanced stoichiometry. And I forgot one. Need to be AB. Okay, AB. Make sure it's going to be AB functional groups. And also the AB repeats units. This is assumptions. But then there will be a question: how to make the high conversion or balanced stoichiometry in practice? And how to make sure we take them? Okay, first is the repeat unit assumptions. We make sure that our repeat unit is 80 repeat units, and we can adjust our monomers according to this result. And we make sure the stoichiometric balance. And I think we can get in practice. But there will be another let's say another method to help. Okay, to help to get the linear step polymerizations will be successful. So the idea is, because there will be many constraints from the polymer itself, they need to develop some method. Okay, let me just make it quick. So first is, we need to make sure if there is the transesterification. Okay, so this is a thing in the polyester. Okay, so we need to make sure that this is the linkage between the carboxylic acid or diacid to the diols. There will be some reaction here to make this happen. Okay. Also for other as well, this is the making the ester. Also for this part as well. Okay. So we say this is the ester interchange. And then the second one is the malpolymerization, or if we want to write here, we can make sure that adjust functional group. This is what I've said. We need to adjust functional groups to make the repeat units as AB repeat units. Okay. If you look on what we have here, this is A, okay, this is B, and we need to make A, B, okay, B, A, okay, and then it will be our repeat units, and all the same thing. So this is the first one. Okay. So we need to make sure repeat units AB. So adjusting functional groups, and then the second one is using the salt formations. So, anyone remember what's salt formation? Acid, base, salt, right? Remember? From really, I think, high school chemistry. So which means the salt will make sure that all the reactions is stoichiometric, right? Okay. So if you can find salt formations, and you can make some theory on salt formation, you can find monomers that will have balance in stoichiometry. Okay. It means that this will help you to decide which process you want to go. So let me write here. This is to make sure, ensure the balance of stoichiometry. Okay. So again, let me repeat one more time. This is important. So first, the process to make sure that linear step polymerization works. First, you make sure the functional group AB, repeat unit AB. Okay. That's why you need to take AA functional group and BB functional groups. Okay. Or ARB, A or BRA. Okay. Or to make sure that this is AB repeat units. The first thing. Second thing is to make sure the balance of stoichiometry. The method is for the salt formations. Okay. Looking for salt formations. There will be one additional method to help this process. We call the interfacial polymerizations. Okay. So this is the reaction at the interface. If you want to look more, you could find, we call this the Bauman reaction. So this is how it looks like. So focus maybe on the picture on the right side here. So we are going to have two solutions, solution A and B. And between the solution A and B, there will be an interface. And the reactions happen only on this interface. Okay. So let me write here the conditions. So let's say two immiscible solution of monomer at the interface or meet at the interface or melting at the interface. Let's say this is diamine at the water. And the natrium hydroxide and diacid chloride in carbon tetrachloride. One example is this reaction. It's diamine and a chloride. So maybe the first solution is diamine at the water, and the second solution, the solution B, is the chloride. Okay? The chloride is one chloride. So that's the chloride. But I write in the more general terms, as long as it has diamine and water, and the other one is the diazide chloride. This is diazide chloride, right? It has chloride here, diazide chloride. The middle part can be anything. As long as you have the diamine and the dichloride. So this way, using the interfacial polymerization, so we are make sure that this interface is the one that polymerization happens. The polymerization takes place on this interface, and then if you look, I think I can show you later, just giving you some links to the video, how it looks like. This is how we make the nylons. If you want to make a nylon by yourself, you can make this approach. So take these two solutions, and then maybe put some metals or maybe some rods. So you put the rods inside, and then take outside, and then it will be forming the fiber, and you can collect the fiber, and that is your nylon. And this interfacial also helps to make sure that the polymer chain is formed. Okay, let me write some summary. Let me write here summary of the step growth. I forgot to add one more page, or let me add one more page. Okay, let me add first. Wait a moment. Let me add. Delete this, and okay, so summary. First, they have variable in chemical reactions. In step growth, and then a lot of high performance polymer. And let me rephrase the high performance. Why high performance? Because high performance makes sure the molecular weight is high and pure, the purity of monomers. Okay. And this is also because the high performance, because the functional groups are in the backbone. Yeah, in the backbone. Okay. And then 3, the carothers is a simple method to predict the degree of polymerizations. And then step growth need very high conversion, the P, right? And balance stoichiometry. Balance stoichiometry. Okay, I think this is already conclude all the things we have done. The chemical reactions, I hope for some basic polymers in the step growth, like the polyesters, the nylons, the polycarbonate, and so on. You can use that as your reference for the chemical reactions. Okay, and just remember not all the monomer and polymers, but I think what you need to emphasize is through the reactions, I'm not convincing you to memorize all the reactions, but what you need to memorize is the groups that is reacted. For example, how to make sure that there will be some ester or transesterification from the polyester, or maybe from the nylons, how to make sure that the diamine is reacted, and so on and so forth. Okay? And the high performance polymers, okay, because the result is a high molecular weight for the polymer itself, and the functional groups, they will be in the backbone. Okay? So it's considered to be a high performance polymer. And then the carothers, how to predict the degree of polymerization, okay? Which the degree of polymerization will be depends on the conversion and the stoichiometry. Okay? The stoichiometry here is, if you remember, is the R, the ratio between functional groups A and B. Okay? So we can predict from the R, and then from the B, we can predict how the polymerizations will take place. Okay? And then that's why the typical graph for the polymerizations and for the P, or for the P, is like that. It's really significantly increased exponentially when the P is really a high conversion. Okay, so that's it. The linear step polymerizations. Okay, so this is the end for linear step polymerizations. Okay, any questions? Any question? I think, as I mentioned, the midterm will be consist from the introductions, the principal polymerizations, the step growth, linear, and then later non-linear, and then one more chapter, the chain growth. That will be content for the midterm. Okay. The midterm, you can have your notes, okay? A4 notes. So I hope from all the lectures and all the discussion that I give you, the assignments, I hope you still remember that, and then you can elaborate in your notes what reactions you want to write, or maybe some notes, which one is you think important, okay? And yeah, I think that's for the notes. Okay, I think one more section for today's class is just a little bit introduction on the nonlinear, just a few slides. So I think I will stop this presentations, and then let's go to the second polymer. Oh, it should be polymer synthesis 2. I forgot to change the title. So we are going to work on this parts here. It's a little bit, it's not as heavy as the previous one actually. The heavy one is from the theory, because in the nonlinear, we are not thinking on a linear polymer change. We are thinking on a network. It's not linear. So we start from the definition, some example, some theory, and what will happen if we have the dendrimers and then the hyperbranch. I already write here suppressing deletions. Okay? So, and that will be the contents. So to start with, we start with the monomer that has functionality greater than 2. Okay? If you remember, in the linear, we have a difunctional monomer, right? And now, if we have 2, greater than 2, for the functionality, the consequences is we will have a branch structure. We have a branch structure. Okay? And then what will happen is the molar mass will be increased because of the another structure in the branch. Okay? And if you compare with the linear step polymerization, of course it will be increasing in molar mass. Okay? So that's the idea on nonlinear step growth polymerizations. Okay, and then if you further branching the structure, it will be, we say, a complex network structure. Like for example, if we have, let's say we have AA and we have B, B, B. So we have 3 functional groups B and 2 functional groups A. Okay, if we plus these 2, what will happen? If we imagine that this is only difunctional AABB, if there is no B here, we know they will be linear. But if we add one more here, and then maybe add one more here, maybe B can be 4, it will be giving us the different structure. So for example, let's say this is going to be 4B like that to give so this B, okay, and then connected with A, and then connected with B again, and then connected with A, and then A is going to be down here also, and then it's connected also, and connected there, and then connected again. Okay, So if you see here, we have a network. Okay, we have a network. So this is what we call the polymer networks. And mostly, this will be, in the property, this will be thermoset. And what will happen in here, at these interconnections, the interconnection is really close. So in between this chain, they are actually really close, which means that when it starts polymerized, it's not easy to, like for example, if we are in a thermoplastic, if we melt, we can reproduce again, right? We can mold again. But here, because it's already fixed in this point, we call this as a gel point, the thermoset cannot be reproduced. Or if we heat, if we take into, if we melt the polymers, we cannot make the same polymers. So it stays as it is. Okay, what else do we have? Yeah, this is what we have. We call the gel point. This is the point at which the first network is formed. Okay, it's the branching one. Okay, the branching. In this case, you see here there is some dots in between of the chain. That is the gel point, the one that is connected each other. And the process is called gelation. Okay, gelation. Okay, I think I will stop under here. Okay, and we continue. Thursday, we have class Thursday. We have class this Thursday. We have class on the morning. So I hope we can continue on Thursday. Okay. So that's all for today.